Okay, well, hello everyone. We just did a couple of hour Q&A about physics and mathematics and more technical kinds of issues about our models of fundamental physics. We're now going to turn to talking about philosophy and general kinds of philosophical issues about finding fundamental theory of physics and about our particular model. So, we had a few questions queued up here. Let me take a look at them. All right. First question here was about determinism versus this is a question of deterministic universe is dull and the concept of free will or even time itself will be moot. So I'm not quite sure. Let me try and address that a little bit. So in our model, it is indeed the case that there is a deterministic evolution for the whole universe. It's a little bit more complicated because it's this multi-way evolution that takes account of sort of all the possible branches of quantum processes. But in the end, there's a definite rule that starts from the beginning of the universe and computes what will happen in the universe up to the point where I'm talking to you here now. Now, the issue is, does that mean that what is happening in the universe is somehow determined in a way that denies the possibility of, for example, free will? And the answer is no. And the reason is this phenomenon I call computational irreducibility. The fact that even though you know the rules by which you can in principle compute everything that's going to happen, there is no fast way to do that. The only way to compute what's going to happen is to essentially follow each step in the computation and see what it leads to. And particularly when we're talking about a computation that represents the universe, where would we get to run that computation? How would we run the computation that is the universe, unless we could have a sort of a computational shortcut to the computation? We don't get to run a computation of the same length as the one that is our universe in any way that shortcuts it, because the only place we have to run the computation is the universe itself. So we have both the sort of mathematical result of computational irreducibility, that there isn't a way to shortcut the actual process of working out what will happen to just get to the answer, to say, for example, in traditional science, computational reducibility was a big thing. And traditional mathematical science, some of its great triumphs were computational reducibility. You know, what Newton did working out, the orbits of planets and things like that. That was significant because it allowed you to figure out where would Halley's Comet be n revolutions in the future without having to effectively just trace every step of Halley's Comet orbit. You could just say there's a formula for what will happen, and the answer after however many revolutions will be this. So that's a typical example of computational reducibility. What I found in the 80s actually was that it's very common to have this phenomenon of computational irreducibility, where even though the rules underneath are deterministic and perhaps simple, the actual behavior itself can't be determined except effectively by just following every step in those rules. There's no way to shortcut what happens. So once there's no way to shortcut what happens, you're stuck with saying, well, I've got a faster computer than you, and what takes you 2 steps to, what takes you 2 nanoseconds to run on your computer, just because I've got faster silicon in my computer takes 1 nanosecond to run on my computer. But that argument of just I've got a faster computer, faster not because it is doing something cleverer, but faster just because its clock speed is higher, that argument is just not going to wash when the thing that you are trying to simulate is the whole universe, because the thing that you are doing the simulation on can itself only just be our universe. And so that's why once there's computational reducibility, there's a fundamental sense in which you can't work out what the universe will do except by effectively watching the universe do it. So in that sense, while there may be determinism, it's not useful determinism. It's not determinism which would allow you to predict what will happen. You still have to just watch and see what happens. Okay, how does this relate to things like free will as we think about it for people, for example? So one way to think about this is when we have underlying deterministic rules, there's the question of whether the behavior of something that operates underneath, according to those deterministic rules, appears to be free of those deterministic rules, or is it sort of locked down by those deterministic rules? If you imagine, I kind of often use the analogy of the 1950s science fiction robot, where you could kind of trick it by getting it stuck in some simple logical paradox or something. We don't think that's in that case. There's a very small sort of amount of computation between the underlying rules and the actual behavior of the robot. In the case of computational irreducibility, there's often there's a sort of irreducibly large gap between the underlying rules, those simple logical operations, and the actual thing the robot does. And so in some sense, we would say that the thing the robot does is sort of irreducibly far away from those underlying deterministic rules. There is underlying determinism, but the actual behavior is irreducibly far away. Now, you can ask questions like, how does free will, in this sense, there's sort of a question of responsibility and its relationship to free will. So here's two models for how an organism might work. One model is let's say you're asked, why did you do that? Okay, well, one answer is, well, it was because of something that happened to me from outside. It was not something intrinsic to me. It was not some intrinsic computation happening in me that caused me to do whatever I did. It was a thing that came from outside. I did that. The self-driving car, drove into this truck because from the outside, my sensors picked up some fast-moving, endangered animal that was about to jump into the road. And so something from outside of me caused me to do what I did. That's kind of model number one. Model number two, the self-driving car, did what I did because of something to do with my internal programming, because of some AI algorithm inside me caused me to do this or that. So one question you might ask is, in which case is the self-driving car more responsible for what happened? You would probably say it's in the case where it was that internal algorithm that caused it to do what it did. And that's kind of the analogy with free will as a result of computational irreducibility, is free will that comes from inside the organism, so to speak. Inside, there is an irreducible computation happening inside the organism, and that's what's causing it to do what it does, not, I did it because of sort of randomness from the outside. By the way, this is something that comes up. I did some testimony for the US Senate last year about AI content selection for things like news feeds and so on in social media and search engines and other kinds of places. And this question of the AI picked what it wanted to show me. And the question is sort of, how do you assign one of the ways to think about this is, how do you sort of assign responsibility for what the AI does? And is it something where there is where the AI in some sense has free will? So there was a possible piece of legislation that basically said, we'll insist that the AI that you make visible the code for the AI, and then we'll be able to say, is the code okay or not? Is the code doing what we want or not? Well, and one of the points I had to make was, look, that's just not going to work. Because of computational irreducibility, just because you know what the code says doesn't mean you can know what the thing is going to do. It has, in some sense, that's the practical version of sort of free will for AIs playing out. So that's kind of a long answer to the question about free will versus determinism. Okay, there's a question here from William Yam. Why is there anything? That's a really good question. I have thought about it a bunch. I don't know the answer. I think the first question is, so, here's a possible answer. That's a kind of a last week's thought about this question. So existence, okay, this is sort of an attempt, and I don't think it's going to get all the way there. Kind of, why is there something rather than nothing? Why does the universe exist? Okay, here's a possible way to think about that. The way to think about it is that we are entities within the universe, and we are trying to talk about the question of why the universe exists. So here's a possible analogy. If we think about mathematics, and we are operating within an axiom system in mathematics, let's say the axioms of arithmetic or something, then we can ask the question, is this axiom system consistent, let's say? And it's Gödel's second incompleteness theorem that says, from within those axioms, we can never prove or disprove the consistency of these axioms. In other words, from within the system itself, we can never prove or disprove the sort of the overall story of that system, in that case, consistency. So I have this slight suspicion that it might be possible to show that for an entity embedded in a universe, it is this question of existence is in some sense undecidable for an entity embedded within a universe. And that's not a very good answer, because it's just saying that there will never be, that the question of whether the universe exists is somehow a question independent of anything that would be sort of axiomatically defined by the rules of the universe as set up for an entity that exists in that universe. It's not a great answer, but I have to say, in the history of philosophy, there aren't a lot of great answers to that question. And I think this direction for trying to find an answer may be one of the more promising ones. And it's, you really have, that question really hits you right in the face once you start to have a serious chance at having a fundamental theory of physics. I mean, the other big question is this, that in a sense, by having a fundamental theory of physics, we're turning physics into a branch of mathematics. Mathematics is a system of abstract development. You're given some axioms, you work out their consequences. We've always assumed that physics is not like that. That it's something where we're progressively approximating how the world works. We're not thinking somebody will just present us with axioms and just say, this is the world. Now go work out what consequences that has. Actually, interestingly, it was Hilbert's sixth problem, when Hilbert defined these problems that might sort of be interesting for the future of mathematics back in 1900, I think. Hilbert's sixth problem is very simply stated. It's like, find an axiomatic representation of physics. And in a sense, that's what we're trying to do, is to find a rule which defines physics. Hilbert had a slightly different meaning for that, but this is kind of a conceptual, a modern conceptual extension of what Hilbert was talking about. So in a sense, when we're reducing physics to mathematics, there will be a question of, okay, so you've turned it into mathematics. You've turned the operation of the universe into something like computing the digits of pi. You've turned it into something which is a purely abstract mathematical operation. And it's fine to say the abstract mathematical operation in some sense is, let's say, happenable. It can happen. 2 + 2 can turn into 4. It's a purely inexorable mathematical thing that those two those two things are equivalent, that you can do this operation and so on. Now the question is, why is it actualized? What causes it to be the case that just because you could compute the digits of pi, and this is how it works, why does that actually happen? Why is there an actualness to that occurring? And that kind of turns into these questions that I think in the history of philosophy and theology have turned into these questions about the existence of a prime mover, the thing that causes everything to be actualized. And my impression is that the progress on that question in philosophy has not been very, very great. And I think that, again, that's what sort of swirls around this kind of possibility that for entities embedded within the system, there may be an undecidability to answering that kind of question, which sounds like a terrible wimp out, but I think it might be possible to get a much more precise version of that, the precise sense in which that question is fundamentally, it's like in Gödel's theorem, where one says, you could ask the question, oh, I don't know, you could ask a question about some equation involving integers, and it might be the case that that question is simply independent of the axioms that you've defined for arithmetic. It could be the case that that question is, it could be true or it could be not true. It's not determinable from the axioms you've defined. And I think there are a lot of very real questions in mathematics where that will be the case, but that's a different topic. Okay, let's see. Do you see the potential for eventually detecting self-replicators per end life within one of these rules? Well, your parenthesis, I think, has a deep amount of content hidden in it, so to speak. Self-replication is not a difficult thing to get in a computational system. Does self-replication equate to life? I don't think so. I think the definition of life is a slippery one, and you know, okay, a thing I like to remember, when I was a kid, the first Mars landing spacecraft was sent off. And of course, when you send a spacecraft to Mars, one of the questions is, does it find life there? Back when I was a kid, it still seemed pretty likely that there would be life easily findable on Mars. So the question is, what instruments do you put into your spacecraft to detect life? And you know, you might have a camera to see if little critters come up and say hello to the spacecraft webcam type thing, or whether or you might have something which detects some other property of what you find on Mars to determine is it alive. And actually, back in those days, one of the more popular properties was you feed it sugar and you see if it eats it, basically, if it metabolizes. And there was some other very bizarre ones I never really understood very well. I haven't really looked at these since I was a kid, but there was one to do with the catalysis of oxygen-18, whether oxygen-18 was a successful catalyzer as well as oxygen-16. There was another one to do with optical rotation, whether you got an unequal number of left and right-handed molecules, those kinds of things. So the question that one asks oneself is, okay, is life all about liking sugar, so to speak? And I think the answer one would reasonably say is, no, that's not a good abstract definition of life. The question is, what is the abstract definition of life? That's really hard to decide because we only have one example of life. It's just life on Earth. And all life on Earth basically came from a common ancestor. All life that exists today basically came from a common ancestor of some kind that involved RNA and you know, all kinds of cell membranes and all sorts of other things. So we don't have a generalization of the notion of life that, for example, allows us to tell, you know, is that strange thing that exists in, you know, on Europa or something, should we think of that as alive more or less than we thought of a stromatolite from you know, from Precambrian period as being alive? And you know, as I say, on Earth, the definition of life is incredibly historical and incredibly specific. What is its generalization? We don't really know. And its generalization certainly isn't just self-replication. But there's sort of a question for, you know, even in things like cellular automata, which are much more rigid kind of versions of sort of simple rules, it is not difficult to get self-replicating, to get things which look exciting as self-replicators because they're not trivial. There are cellular automata that trivially have self-replication, but there are other ones where you have to go to a lot of effort to get a self-replicator, but then you can get one. And that sort of feels a little bit more like the case of life. I mean, to mention something historical, you know, when John von Neumann, there were several different origins to the idea of cellular automata, but one of them was John von Neumann in the 1950s, early 1950s, was interested in sort of mathematicizing the notion of life. And so he tried to sort of idealize what he thought of was the kind of the chemical soup that represented life, and he ended up his friend Oscar Morgenstern of economic game theory fame, and then another person, Stan Ulam, of hydrogen bomb fame, actually, sort of in different ways suggested to von Neumann, oh, you should consider these discrete systems. But then, which turn out to be like, in his case, like two-dimensional cellular automata. But von Neumann was so convinced that getting self-replication was hard that he ended up constructing this incredibly elaborate cellular automaton-like thing with, I forget, I think it was a 26,000 cell configuration of this very complicated thing with huge numbers of rules and so on to get self-replication. And they thought, gosh, this is like life, because it was hard to get and it self-replicated. But actually, I don't think self-replication is a great test for the existence of life. I think in the end, there is no bright line of what is abstract life beyond the statement that it is sophisticated computation. That's a kind of a necessary feature for anything that one would reasonably call life, is that it not be computationally trivial. And I think really the operational definition of life is its computation operating at a molecular scale. And that happens all over the place. But we are, the computation that happens at a molecular scale in us is a little bit more understandable than sort of computation happening at a molecular scale in a generic, fluid or something like this. Of course, it's not completely understandable, or we would have solved all of medicine, but that's a separate issue. Oh my gosh, this is now going to show me up as a non-professional in philosophy. Is the model substantivalist or relationist? Is it background independent? I wonder whether Jonathan might happen to know from his philosophy background what those. I'm sorry, it's really embarrassing because my mother was actually a philosophy professor in Oxford, and so I was exposed when I was a kid to lots of kind of analytic philosophy kinds of things, and I'm sort of just embarrassed that because as a kid I always said, if there's one thing I'll never do when I'm grown up, it's be a philosopher. That I probably didn't pay as much attention as I should have done. But okay, Jonathan, can you translate those terms? Do you know the?
Yes, yeah, and I think the answer is that it's. Let me get this right.
Tell us what the terms mean.
Okay, so relational. Okay, to my understanding, relationalism is the notion that there is no such thing as a background space. That basically all that your fundamental ontology is just relations of material objects to each other. And substantivalism is the statement that there actually exists a background space in addition to the material objects and their relations. I think what we're proposing is basically substantivalism modulo relationism, or possibly the other way around, where
we basically, I would think that
we only have background space, and the relationalist stuff emerges from it. Would be my. Maybe you have.
Well, okay. So one feature of these models is space is all there is. There is in a sense. Everything about the universe is made of one kind of thing. And it's that kind of thing turned into sort of the configurations of that one kind of thing define all the things that we see in the universe. So in that sense, it is. It sounds like it's a substantivalist kind of thing. On the other hand, that thing is not a thing in the sense that one is used to talking about things, because we're used to talking about, the physical object that is, that has an actual, that sort of has pieces that it's constructed of and so on. And what we're talking about is space being made from discrete points, where the only thing you know about those points is how those points relate to other points. There's no sense in which there is a kind of a background to space that is independent of the existence of the points in space. In other words, space is made of its points and their relations. It is not something where there is sort of a background and where things live within that background. But on the other hand, the background, the space is everything. It's not that something, so there's neither a background that is outside of the model, but it's also the model is all about space itself. Okay, given different rules that may govern a structure, is it possible to derive conflicting results within the proposed theory. Okay, that's interesting. So in a sense, the uncertainty principle and other things in quantum mechanics are like deriving conflicting results. In a sense, the fact that there is quantum mechanics is the consequence that, at least temporarily, there can be conflicting conclusions about the way the world is working. And I think that's probably the best way to say that. Do you think there exists an elsewhere outside the universe where the computation of this universe takes place? I don't think so. I think this model is a representation of how our universe works, and there's no substrate on which this model is being run. It is this abstraction that is, the model is an abstraction of how the universe works, and it's that the universe just does these things according to the model. It's not that the model is operating on an elsewhere, as you put it, that doesn't exist within an elsewhere. It just is this sort of this thing. Now, having said that, it's sort of interesting to think about that as a yeah. I mean, I think, as I say, I think that the main point is just the model is a representation of what the universe is doing. So there's no sort of necessity to say, what does the model live on top of? And there's no kind of, it's living on the back of a turtle and then its turtles all the way down type thing. It's just, this is the thing that is a representation of what goes on in our universe. Jacob, consciousness question. Is there any place for human intentionality to change, or at least to shift, the probability of which pathway the deterministic universe will take? Sorry, don't think so. I mean, I think the answer is that in this, well, it's a little bit complicated, because in this model, things are determined. The evolution of the universe, okay, there are these quantum branches and things, but the sort of the super description of things is completely determined. And there's no way to say that the universe just is what it is and it does what it does. Now, what does that mean for our perception of consciousness and so on? So and I'm not sure, that there's more to figure out here about how to think about this. But one of the things that's kind of new for me is thinking about this notion of these different reference frames, these different description languages that we can use to understand what's happening in the universe. This idea of this rule-space relativity idea, that there can be many different ways to describe the universe, which in some sense are equivalent, but they're nevertheless locally, their actual description, the actual experience of those things is different. And so I think that there's a sort of the choice aspect of dealing with the universe, maybe more in the sense of this description language, that there is at some underlying level, there's kind of a sort of a version of what's going on, but then you have a way to understand what's going on, and your description, your way of understanding it, is sort of arbitrary. So, in other words, the particular, put it this way, the particular firings of neurons in your brain, those are determined by the way the universe works. But if you were to look from the outside and you were kind of to write down a narrative of what's happening in your brain, there might be many different narratives that you could write down. And those narratives are kind of the meta description of what's happening. And I think there's freedom in that meta description. It's not a freedom in how your neurons fire, but it's a freedom in the representation of what it means for your neurons to fire in that particular way. That's my best understanding of that right now. I think it's really quite interesting that these different kind of reference frames, these different description languages for representing the universe might give one a way to really understand these different sort of approaches that people have developed for making sense of the world, so to speak, from the the sort of very scientific approaches to making sense of the world, to more sort of psychologically oriented approaches to making sense of the world. And these things are there. They can still describe the same world, but in different ways. And by the way, the ones that we have that came out of our biological evolution, our senses and things like that, are probably this very, very, very microscopic corner of all the possible descriptions one can have of the world. And for the putative aliens, so to speak, one could imagine vastly, bizarrely incoherent descriptions of the world that are in some sense still describing the same world underneath. Okay, from Ted here. Wait a minute. Oh, we got that one already. From Andrew. How do these models relate to the Archimedean and Platonic solids in sacred geometry? Boy, it's convenient that on my desk I happen to have from a whole different live stream I was doing. I happen to conveniently have a little Platonic solid here. Well, so I don't completely know what sacred geometry. I've sort of heard of that, and I don't really know what that is. But back in antiquity, there were a bunch of theories about the world being made from Platonic solids, for example. And for example, this guy, the dodecahedron, was represented quintessence as maybe the thing from which the heavens were made, so to speak, if I remember correctly. The question of whether there is I think the thing I would say is that kind of theory of the world is made of Platonic solids is a fascinating allegory for the kind of thing that we're now doing, projected back into the kinds of things that people knew about in antiquity. I mean, in antiquity, the very notion that the world might be made of a set of identical elements, that would be where the arrangements of those identical elements might lead to the world as we know it. That's a super interesting notion that found another place in atomic theory and so on. And we're, in a sense, continuing that tradition. We're saying the world is made of these identical elements and their connectivity and so on. So in a sense, we're continuing a tradition that started with people like Democritus, pre-Socratic philosophers and so on, and that was sort of submerged in some sense in the kind of deluge of let's describe everything in terms of mathematical equations, where it isn't so much of a kind of a structural understanding of what's going on. So in that sense, I think there's some resonance with those things, although the ancient Greeks didn't have computers and didn't have, well, they might have had the Antikythera device, which was a kind of a mechanical computer-like thing, and maybe those things were actually fairly common, but they didn't have, the thing that is really, in my lifetime, for example, has been really a dramatic thing, is the fact that computation is now so ubiquitous in our world that we can start to get real intuition about how things work computationally, and that just didn't exist before. And that's, I think, why, insofar as we've been able to make some progress here, that was not really accessible to, for example, the people a century ago who kind of initiated the dominant theories in physics today, general relativity, quantum field theory, those kinds of things. At that time, nobody was thinking about things in terms of computers. The Turing machine was still, when general relativity was invented in 1915, the Turing machine was 21 years in the future. And even when Turing machines had been invented, people didn't take them seriously for physics until perhaps even my own work in the 1980s. So it took, when Turing machines were first invented, the first point was that it just wasn't clear how general Turing machines were. It wasn't clear that, did Alan Turing's original idea was, let me idealize, what bank clerks do and try and make that into something that can be mathematicized. And, when Gödel had done what amounted to the same thing in 1931 with Gödel's theorem, he has this wonderful footnote that says that, Gödel's theorem, which was sort of essentially a way to turn arithmetic into something computationally in which you could program other things, that maybe this doesn't apply to human minds. And he has some bizarre footnote about how this could correspond to the Russell's theory of types, but not ordinary types. Types, I think he says something about ramified into the transfinite, which, I mean, we can decode what that means, but it's just kind of, he had the idea that the human mind is somehow much more infinite than the kinds of things that he was describing in Gödel's theorem. And so it just wasn't clear that physical kinds of things like human brains and so on would be subject to the same kind of mathematicization, the same kind of idealized representation as the things that occurred in Gödel's theorem or occurred in Turing machines. And that was an idea that really didn't exist. I mean, back when I started talking about this in the 1980s, people were saying, you're just wrong. It can't possibly be that way. You know, we know that physics is governed by partial differential equations that represent continuous effects of this on that and so on. You just can't represent that with a Turing machine. I think that has become gradually, less of a shocking thing, and the idea that that there could be this generality to computation has become more popular. And I think now with this model that we have, I am now certain. There's no doubt in my mind the universe is computational and is of sort of equivalent power to something like a Turing machine. I think the how do we get to all of that? I was talking about why the ancient Greeks couldn't have come up with the theory that we have, and the real answer, I think, is that the intuition about computation, the idea of computational irreducibility, for example, just didn't exist. It even didn't exist even Alan Turing didn't have the idea of computational irreducibility, really. He proved the undecidability of the halting problem. He proved that you couldn't, in a finite time, generally work out what a Turing machine will do after an infinite time. But somewhat amusingly, the very first program ever written for a universal computer, which was in Alan Turing's original paper, is full of bugs. And bugs are kind of one of the practical manifestations of computational irreducibility. You can't readily predict what your program will do just from seeing what the rules are, so to speak. And that's so in a sense, the intuition that there might be bugs, the intuition of that typical programs behave in ways that are hard to predict, is an intuition which really, I mean, for me, arose from experiments that I did in the 1980s of actually looking at computational processes and seeing what they did. And it was a big surprise to me that was a phenomenon that was ubiquitous. I thought maybe there would be some very special computation you could set up where you could get undecidability or something. But no, actually, it's a ubiquitous thing. And that's an intuition that just is, I think, a new intuition that we just didn't have until very recent times. I mean, I kind of view that intuitional realization that you can get very complicated behavior from very simple rules, that you can get phenomenon of computational irreducibility, that's what kind of unlocks the possibility of the kind of theory we're talking about now. I mean, there were a few other sort of things I mentioned before, maybe I'll talk about it later, the sort of the wrong turn of equating the nature of time to being like the nature of space. All right, let's keep going here. Okay, Brian on the live stream. If the universe is deterministic, does that mean we will access all the hidden variables? That's a complicated story because, in other words, could we ever know sort of exactly how a universe will evolve? Well, the answer is not in practice, because even to go measure, that's an interesting point, actually. I mean, to go as an entity within this universe, to go collect all the data to know the state of the universe everywhere is not something we can do. We can't do that for reasons of, it's an interesting point, actually, interesting point. Worth nailing that down a bit more carefully. But the basic point would be, if you think about the causal graph, we sort of live in the causal graph. So the events that correspond to the actions that we take are events that exist in the causal graph, and they can affect other events in the causal graph. But if our goal is to go sample the whole universe, go know what the state of the whole universe is, and go sort of bring it back to our brain, and then go and evolve forwards, there are many reasons we can't do that, not least because sort of our brain that's going to figure out what the universe is going to do has to exist in the universe, but that, quotes, brain is supposed to be representing the whole universe, and we don't get to represent the whole universe in something smaller than the universe. That fact is another consequence of computational irreducibility, that there's no sort of sub-representation of the whole universe that isn't the universe itself. So I think the answer is that we can't really determine that. Okay, next question. Does your theory depend on the axiom of choice? I really don't think so. So I'm going to hope Jonathan might have a comment on this. But in the so the axiom of choice is something that comes about in sort of formal set theory, and formal set theory one only really cares about that when one is dealing with the truly infinite. And in our model, the universe is big. It might have had 10 to the 500 events in it, but 10 to the 500 is not infinity. And so we don't have to have this kind of axiomatization of infinity that involves things like the axiom of choice. Jonathan, do you have a better comment?
Yeah, so I think our models kind of can't depend on the axiom of choice because they're explicitly constructive. So one of the reasons why the axiom of choice is, well, there are many reasons why the axiom of choice is philosophically sort of controversial in the foundations of mathematics. We know Gödel proved that it was effectively independent of the standard axioms of set theory, ZF set theory. And it sort of corresponds to a statement that's perfectly intuitive until, as Stephen says, you deal with kind of infinite and particularly uncountably infinite sets. And then it implies a bunch of really rather pathological results about the existence of non-measurable sets and things like that. But for a more philosophical reason, it's also very undesirable because there's a general approach to doing mathematics, which is the sort of constructivist or computationalist approach to doing mathematics, where the idea is you don't want to have non-constructive existence proofs. In other words, if I prove something, if I prove a theorem that says there exists a topological space with such and such a property, I should actually be able to construct that space by some finite algorithmic procedure. There should be some finite rule that constructs that space. I don't just want to have an abstract existence proof that says, this thing exists, but I have no idea what it is or how to construct it. And it turns out the standard axioms for mathematics, at least in the finite case, can be made purely constructive as long as one omits the axiom of choice. But the axiom of choice is sort of inconsistent, incompatible with a constructivist formulation of mathematics. Our models are purely constructive because they're explicitly set up to be computational. So in particular, they can't depend on any non-constructivist mathematics like AOC or related things.
Hey, you should define for people axiom of choice, just because some people won't know.
Okay, so the basic idea is if you have a whole bunch of sets, right, and they're non-empty, so each set has some elements in it, then you can define this thing called a choice function, which basically just takes an element from all of those sets and assembles a new set, where you've just chosen an element from each set. And the axiom of choice says that as long as all the sets that you started with were non-empty, this new set that you generate by just choosing one element from each set is itself non-empty. Now, that seems completely intuitively obvious when you're dealing with finite sets or even countably infinite sets. It's completely uncontroversial. If the sets you have are uncountably infinite, then you run into these issues. And then it's much less clear whether the axiom is actually intuitive or whether it's actually wrong. And that's where you get into these constructivist issues.
Okay, next question here from Lex. What are the limits of mathematics and computation? Well, I mean, there's questions about limits within mathematics itself, and there are questions about limits within our universe. So, within mathematics itself, we already know from things like Gödel's theorem that there exist statements that can be written down that sound mathematical, that are simply not accessible by the axiomatic system that is defined in mathematics. So Gödel originally had this statement is unprovable, and his main work involved showing that this statement is unprovable could effectively be compiled into a bunch of statements about mathematical equations involving integers that were visibly things that were sort of within the domain of sort of theoretical arithmetic to investigate. And so there are things there where there are statements that turn out to be mathematical, that statements of mathematics that are independent of the axioms as we've set them up in mathematics. Now, one thing to say is that mathematics, as it has normally been practiced since about the 1880s or so, has been on this axiomatic kick. Okay, what does that mean? It means, one says, just build mathematics as a kind of logical system, or one just says, assert that the following things are true. Then what follows from that? In the earlier history of mathematics, I think mathematics viewed itself as being much more an idealized description of the real world. You know, I think Euclid, although he did write down axioms, he thought those axioms were just idealizations, were just sort of precise versions of what was just true about the world. Things like two parallel lines can't cross, which Euclid thought was just a true statement about the world that he was making precise so that he could build a logical system, but he didn't think that he was asserting that just as an arbitrary thing. I mean, what Jonathan was just mentioning about the axiom of choice, that's an example of something where somebody can just say, you know, we choose to make it true, we choose to make it not true. We don't have any intrinsic reason because of the way the world works for us to choose one thing or the other. And so something that started around the 1880s was people just saying, just imagine it works this way, just set up these axioms, then see what we can prove from that. And one feature of axioms is that they will be things where the axioms just don't have anything to say about. The axioms just are, something could be true, not true. You just can't prove it from the axioms. The axioms only define a certain set of things. Now, for example, Gödel ran into that because Gödel was most interested in the sort of understanding the theoretical implications of Peano's axioms for arithmetic. And so, for example, when we do arithmetic, we think we know what integers are. And, you know, we can just count them on our fingers and things like that. But when we're dealing with the infinite, we can't count on our fingers because we only have a finite number of fingers. And so it gets a little bit more complicated. And one of the consequences of Gödel's theorem, so the Peano axioms say things like, you know, for any things that numbers, you know, x plus y is equal to y plus x, or some slightly more complicated criteria involving functions and recursion and things like this, or induction rather. And one way to think about those axioms is to say, we are talking about these things, x, y, whatever, and we are talking about those things which obey these particular axioms. Okay, show me one of those things. Well, one example of one of those things are the ordinary integers that we can count on our fingers. But one of the things that Gödel showed is that there are non-standard arithmetics. There are things that obey the axioms of Peano arithmetic, but they're not like our ordinary integers at all. In fact, they are totally bizarre. They have non-computable versions of addition and all kinds of weird things like that. But what Gödel showed is that there is no finite axiom system that you can ever hope to construct that has the feature that it will constrain you to get the integers and nothing but the integers. So in other words, it's this idea of axiomatization where you're saying, let's take a system and let's make constraints on the system, and let's hope that then with those constraints, the system describes only the kinds of things we're talking about. That's the way of doing mathematics that's been popular for 120 years or so, at least at a formal level. But it's a weird way to do things. It's a very sort of, in my view, rather backwards way to do things. The alternative is just to say, I've got these rules. The alternative, which is much more the computational view, is I've got these rules, now just run them. And that's what we're talking about in this theory of the universe, is we've got these rules, now just go run them. So it's, and so we can ask the question then, can we, you know, to what extent is axiomatization limited? If axiomatization means the way mathematics, then there are limitations on axiomatization. For example, in the theory of computation, the P versus NP problem, the question of whether, for example, NP-complete problems that, I was going to say like factoring, except factoring isn't known to be NP-complete, but problems that are NP problems, whether they can be done in polynomial time, big sort of story and issue for whether you know, public key cryptography is secure, et cetera, et cetera, et cetera. That question of P versus NP I think might be undecidable with respect to the most obvious axiomatization of arbitrary, of infinite computation, so to speak. That's an example of where, but those are theoretical limitations. Those are limitations from within the system itself about how sort of what's provable axiomatically. Then there are questions. Okay, so let's take a question in physics. Okay, first point is, if we're right that we're on our path to finding the fundamental theory of physics, we just turned physics into a sort of, in a sense, a logical system where we can just take the rules of physics and deduce everything that happens. But now you'll ask me, okay, so given that, can you determine whether warp drive is possible? You know, faster than light travel or something like that. Can you prove that faster than light travel isn't possible? Well, maybe we can. Maybe there's a straightforward proof, but maybe it is arbitrarily difficult to determine that. Maybe we can imagine some bizarre collection of masses and processes that go on in the universe, and we can assemble this giant machine, and in the end, the giant machine will make a warp drive, right? And so can we prove that there is no way to assemble the giant machine? Well, that turns out to be something that is kind of a Gödel's theorem-like question. That's something that is ensnared in computational irreducibility. Does there exist this configuration? Does there exist this way to take this, does there exist a solution to this equation involving integers? Does there exist a way to take these tiles and cover the infinite plane with them? These are questions which can have, does there exist any such thing, may not have may have an answer that is arbitrarily difficult to determine in an axiomatic system. Now, having said that, in our universe, it's big, but in the current estimates we have, maybe it has 10 to the 400 elements. 10 to the 400 is not infinity. So in fact, it becomes a completely in principle determinable thing, whether it's possible to make that warp drive. Because what you could in principle do is you can enumerate, in principle, all possible configurations of those 10 to the 400 elements. And you could just say, are any of these warp drive? If no, we can't make a warp drive in our universe. If yes, we succeeded. Now, the problem is, if you think about how would you actually do that? Well, there might be, you know, whatever it is, you know, 10 to the 400 configurations, or what 10 to the 400 to the 10 to the 400, whatever it is, configurations of that system. It's incredibly huge, and there's absolutely no way we could possibly run that computation in our universe. So there might be, in some sense, the undecidability of the existence of warp drive, for example, might be something that is both something that we can say for an infinite, if we allow sort of, we can have no upper bound on how difficult it might be to determine, to find a warp drive. And then we could say that within our universe, it's not accessible just because our universe has a finite number of elements in it. So I think that's, I mean, there's probably more to say about that, but that would be my first cut about sort of limits to mathematics and computation. I mean, I think that at least at a very theoretical level. Did Jonathan want to add something there?
Well, I was just thinking we could mention something about this new kind of proof that's a sort of possible byproduct of rule space geometry. So this is something that Stephen and I discussed, I think only a few weeks ago now. It's a relatively new idea, relatively unformed. But the idea is, you know, rule space effectively contains not just our universe, but you know, different branches correspond to different possible. You can think of them as either corresponding to different encodings of our universe or different candidate universes. And one possibility is you can think of, if you prove a result in mathematics, you can think of it as being proved for a particular physics, a particular physical universe. But rule space contains sort of the set of all possible physicses. So in other words, if you can prove a statement and effectively quantify it over the entirety of rule space, you're quantifying over all possible physicses. The one interesting sort of philosophy of math question is, does that correspond to a valid proof that sort of theorem is true in some mathematical sense that's independent of physics? And we have some ideas about sort of various complexity theoretic theorems that you might be able to prove in this way. And I think we came up with a sort of preliminary name of Leibnizian exhaustion as this new method of mathematical proof, right? So it's Leibnizian because you're talking about kind of all possible worlds, and it's the sort of analog of these mathematical proofs by exhaustion, because you're quantifying over the space of all possible physics as a way of proving a statement about pure mathematics.
Yeah, that's an interesting point, which I had almost forgotten, even though that was only a couple of weeks ago or something. But yeah, this notion, when you say you're quantifying over all possible integers or all possible functions on integers, this is a bizarre twist. We're quantifying over all possible physicses, you know, what is the status of a thing that is true in all possible worlds, so to speak, and what is the notion of truth in something where for any possible physics this will be true? But does it mean it's really true, or does that mean, you know, could it be the case that that there would be some for example, if there's a hypercomputer in the picture, then it won't be true. Then our quantification over universes wouldn't capture that. So the question then is, when there are, and I think that could be thought about in terms of I never remember how these all work, sigma n, pi n type sentences in mathematical logic, that we can think about those kinds of quantifications as being like quantifications that include either all possible computational universes or all possible hypercomputational universes, which then lead to a different kind of thing. Okay, Barry is asking, the hypergraph reduces to some initial condition. Is there something special about the initial conditions for the universe? So one thing to realize is that you can trade off initial conditions and rules, particularly when you're living in this ruleal space of all possible rules. One of the rules you can make is the rule that makes, for example, something from nothing. So there's sort of a trade-off between rules and initial conditions. And I think there's a whole separate issue of, you know, let's say we find a simple rule for the universe. Maybe the initial condition for the universe with that rule is something quite complicated. I mean, in a sort of science fiction-y weird point of view, what if with this particular simple rule, the initial condition for the universe, I'm just making up a kind of science fiction scenario, but what if the initial condition for the universe is then this giant, you know, sacred text of the universe or something that would be that is the initial condition for the universe? What if in fact the initial condition for the universe is not, with that respect to that rule, something simple, but something very complicated? Now, the bizarre question then is, okay, we've got this thing, we represent it as this hypergraph. We've got the hypergraph that started the universe, and it turns out that with this particular that we then have found this really complicated hypergraph that started the universe. Maybe it has 1 million nodes in it, okay? And we know that the rule that we're using, that rule doesn't apply any further back. This is the starting hypergraph of the universe, and it's really complicated. And we're looking at it. We've got it. It's got 1 million nodes in it. We look at the thing. What the heck is it? And so it's kind of like the archaeology question of, you know, we just found Stonehenge. What the heck is it? We just found this thing out there. What does it mean? Does it have a meaning? Can we attribute a meaning to it? How do we kind of understand what this is? And I think that's sort of I consider it sort of a science fiction scenario, because I don't really think that's how it's going to work out. But it's certainly a bizarre sort of thought. I mean, when people, you know, the bizarre kind of thing, it's the signature of the creator type thing is the initial hypergraph, but I don't think it's going to work out that way. But it's fun to think about, at least. Okay, Spiros is asking, can the existence of parallel universes be proven by your theory? In that case, could it be possible for parallel universes to mingle? So in this theory, in this kind of rule-space relativity theory, well, okay, so a couple of different points. I think we talked about maybe a little bit yesterday. In the spatial hypergraph, it can be the case that pieces of the spatial hypergraph break off. Those broken off pieces of the spatial hypergraph essentially evolve the same as any other piece of the spatial hypergraph. And in fact, you don't even have to break off a piece of the spatial hypergraph. You could just have a causal disconnection in the causal graph, and that causal disconnection is very much like black hole formation. But either way, you can have these separate, sort of separate pieces of universe that have separated off from the main universe and no longer causally connected to the main universe. But the first sort of level is, but they keep evolving according to the same rules as the universe. So they are separated universes, but they're evolving according to the same rules as our ordinary universe. Another question is, what about the possibility of universes with different rules? So, for example, I had always imagined that my big sort of philosophical conundrum for the last 30 years actually had been, let's say we find the rule for the universe. Here it is. We're holding it in our hand. Now we ask, why that rule and not another one? And the most obvious answer would be, well, all possible rules exist somewhere. They're all different universes. They're all running in parallel. We just got assigned universe number 3746 or something. That's our universe that we all exist in. And the others, there are some weird we shouldn't be calling them extraterrestrials. We should be calling them extra universals or something. Folks who live in a different universe, who are extra universals, who live in this sort of separate universe and are just doing their thing in their separate universe. So that was kind of the view I had of how it would work out. And then there's this big question, why did we get this rule? Why did they get that rule? And so on. But then what we realized more recently, and I'd sort of had a suspicion about this for a while, that for an entity embedded within the universe, that in a sense, all possible rules were in some sense equivalent. And so in this notion of rule-space relativity, the idea is that you can that all possible rules can be applied, but your view of the universe, your kind of coherent view of the universe, is based on a particular way of kind of slicing this sort of ultra multi-way graph of possible evolutions of the universe. And causal invariance implies that which slicing you choose will ultimately have no consequence, but it will certainly affect the description that you actually give of the universe. So your particular description is something that is particular to you, and there can be other descriptions, but it's all of the same universe. And so I think that this idea of rule-space relativity, in some sense, is a proof that there really is only one universe. But our description of the universe can be utterly incoherently different. So what might have been the extra universals, so to speak, are the kind of extra descriptionals, so to speak, the critters who exist in a universe where their description language is utterly, utterly different from ours. So, a very, very, very simple example of this that is kind of fun to think about and doesn't quite work all the way, but it's kind of fun, is so in our world, one of our principal senses is sight. And the speed of light is quite fast. Speed of light is quite fast compared to the speed at which we can process things in our brains. So when we look out into the world, and we don't look too far away, we don't look at stars and things like that, most of what we see, we sort of synthesize a slice in time as being everywhere in space that we can see at a particular moment in time. That makes sense to synthesize. And we have that sort of view of the world. Okay, so let's say we were dogs, for example, where olfaction, smell, is a much more important sense. Well, so let's imagine, forget the eyes. Just say we do everything by smell. Okay, well, then our view of the world, then it's a little bit of a different situation, because the diffusion time for a smell from 100 feet away is very long compared to the processing speed of a brain. And so it's no longer the case that we can synthesize our world as being this thing that exists in simultaneous time slices where we see sort of a moment in time everywhere in space. That's not what's going to happen. And in fact, one can imagine sort of a version of relativity that would be perceived by a dog, so to speak, where the speed at which sensory data comes from distant places is slow compared to the processing speed of the brain. And so we can start trying to imagine what it's like to be sort of a critter with a different description, with a vastly different description language for the universe. It's sort of humbling to realize that there can be such utterly different description languages that will look nothing like our physics, so to speak, and that will be ways of describing the universe that are nothing like our physics. So in that sense, there can be parallel universes with respect to the perception of the universe, although in the end, the machine code is exactly the same. It's exactly the same universe, but it is this utterly incoherently different. And I mean, one could certainly imagine it's a scenario where, you know, I talked before about how intelligence, life, things like that are really hard to define. And I think they really just boil down to computation, but where you could sort of imagine at sort of a conceptual level saying, well, there's this intelligence, so to speak, that has a completely different sort of perception of the universe from ours, completely incoherent and completely sort of not something we'd pick up in our thinking of physics. So it's sort of an interesting consequence of these kinds of things. But now the question then is, okay, so then the question is, in that case, can you communicate? So is it the case, and it's kind of like the sort of, you know, our communication skills are pretty limited. I mean, we can't even do animals very well. You know, the question of whether, you know, communication involves sort of, it's this issue of can we, outside of our sort of boundaries of sensory information and so on, you know, to what extent can we communicate? You know, communication is typically about, as a practical matter for humans, is about, I've got a thought in my brain, I'm going to turn it into, for example, language, some symbolic representation, and that's going to reform some thought in your brain. We get to do that more directly when we have computational language that can go computer to computer in a way that's a little bit different from the, you know, brain to human language to brain type transformation. In a sense, computational language, and this is part of my sort of what I do for a living and spent my life working on, is kind of the computational language that essentially allows us to encode knowledge in a way that can be sort of passed down, so to speak, in a more efficient fashion than the pure say it and reform the thought in another brain type thing. The kind of, it's a more streamlined form of communication than we're able to do with pure human language and the reforming of thoughts in brains. But this question of communication, can you reform kind of a meaningful, can you sort of reform that thought in a way that's sort of consistent with the way it started off? Well, it sort of depends on the substrate that you're working within. And I wrote this post. Okay, so a little bit of a story. I have a friend named Nova Spivak who's been working on a strange project to put artifacts from our civilization around the solar system, on the grounds that if something bad happens to the Earth, it'd be really good to have the little beacons of this is what we achieved as a civilization out there for the extraterrestrials to pick up long after we're gone. And it's certainly, you know, if you look at the Babylonians, the Egyptians, it's kind of cool how much we know about them based on the artifacts they left behind that describe features of their lives. And so one of the questions is, what can you put out there that is sort of the thing that describes what was achieved in our civilization? And potentially is there sort of an abstract thing that you can put there that sort of expresses the greatness of the achievements of our civilization? And certainly there are details. There are like, well, this is, you know, like the dioramas from, you know, you find in Egyptian pyramids and things of you know, this is what it was like, you know, wooden figures of this is what it was like for a boating party on the Nile back in 2000 BC or something. You know, but the question is, can we do something a bit more abstract? And what would we do? And it's a gruesome business, because if you look even at archaeological artifacts, it's really hard to tell, what did this mean? Is there a translation of meaning from back in those days to today? And by the way, there's nothing to say that what was, you know, there's nothing invariant about meaning. It's something that comes up. I'm sort of veering into some other kinds of philosophy, but in the question of AI, and the question is, so one of the questions that people are often concerned about is, what will AI automate? Will we just automate everything? And one of the points I often make is, one thing we're not going to automate is we can automate the doing of things, but we can't automate the deciding of what the goals are, deciding of what the things we should do are. Because in a sense, the assignment of goals is something, there is no abstract notion of what goals there should be. Goals are something that are the specific of what came out of our biology, our civilization, and so on. They're something that are sort of specific to our own history, so to speak. There's no abstract notion of the goal. It's just like asking, what is the goal of the universe? You know, if we have a theory of the universe, we could say, what is the goal of the universe? I don't think we can answer that in any meaningful way. I think that goals are something that tie back to sort of a human story, a human narrative about what the point was supposed to be. I think I got very far afield. I think I was talking about communicability between sort of different description languages for the universe and sort of beings, in a sense, that might exist with respect to these different description languages. And I think the thing that one of the points I'm making is it's very hard to have sort of a ground truth when your fundamental description of the universe is different. I mean, it's hard enough to have a discussion, you know, when your sort of frame of reference of life is different, to have sort of a discussion across that chasm, even in the human case, let alone when your sort of ground truth about how the universe works is different. It's difficult to see how that kind of communication would work. So that's sort of an answer to the kind of the mingling of communication between sort of these different description languages of what one can think of as parallel universes. Okay, so John Corley is saying, what's happened is, I see. I understand the question. It's sort of God has mathematical vision infinity and is running a manipulate. Yeah, I mean, I think that this whole question of sort of the interaction of theology with the kinds of things we're thinking about, I think is pretty interesting. And I think that one of the things that's really striking to me is if you look at kind of some of the particularly earlier theological writings, I'm no expert in these things, there are a lot of kind of grapplings with questions about sort of what does it mean to have what does it mean for there to be a beginning to the universe? What does it mean for there to be, for example, one of the ones, I think Einstein was a big enthusiast of Spinoza, who had this kind of view that I suppose is summarized as, you know, the universe is the thoughts of God, is a representation of the thoughts of God. And I think that's kind of a very interesting sort of poetic way of thinking about something like what we're sort of talking about, as in there is this inexorable thing that is generating the universe, and we get to sort of see that inexorable process happen as the actual evolution of our universe. And it's kind of the Spinoza version is sort of the operation of the universe is the kind of embodiment of sort of the universe is, in some sense, the actual operation of the universe is kind of the thoughts of God. I think that's kind of an interesting way to think about it. I think that as I say, I think actually I'm hoping to get a friend of mine who's a theologian to join us on one of these live streams, and maybe we can have a more detailed discussion about some of those kinds of questions. I think one of the ones that I'd sort of been hoping that there would be some kind of conceptual framework was this prime mover question of sort of why do you actualize? You know, so okay, so Spinoza's statement, the universe is like the thoughts of God, that's kind of explaining why there's an actualization of the universe. If God exists, then God has thoughts, and those thoughts are our universe. But in a sense, that presupposes that God exists. And the question of why is there something rather than nothing, why are things being actualized, that's a different question. And I'm sort of really curious whether there is sort of a framework for thinking about that. Would you say that it's living on the backs of 4 elephants that live on the back of a giant turtle? You know, I have to say, we in the theory of swag for this project, you know, there's this sort of saying of there's a I don't know. This story is probably apocryphal, but I think it's told about Bertrand Russell. I think he was giving some talk about the universe, and apparently someone came up to him and said, you know, no, you're wrong about this theory of the universe. The universe is all exists on a you know, it's all sort of constructed on the back of a giant turtle. And he was saying, well, what is the turtle standing on? And the person said, well, the turtle is standing on another turtle. He said, well, what's that turtle standing on? Well, said the person, it's turtles all the way down. And that's been a kind of a quote of among scientists, at least, about kind of a view of how things might work. And so we, in the theory of the swag of this project, we were thinking about making some T-shirts about something like it's hypergraphs all the way down, so to speak, or some such other statement. So I think we're not in the we're not in the kind of turtle. Oh, the other thing about that T-shirt, there's a great diversity of different geometrical forms that come out from these hypergraphs, and there are definitely ones that look like turtles. So expect that T-shirt. So Pai Lang says, I asked another streamer about a model platonic solid they had on their windowsill. They said, what? You mean the candle holder? Okay, so I'm more into platonic solids than that. Okay, so I can't read any. I can never read these handles. EHAL is a good exercise actually in semantic. It's a good exercise in segmentation because of where are the words in these handles. But anyway, so E something or other handle. So in your model, how would you describe knowledge? Should we see it as some kind of recurring causal path? Interesting. Okay. So knowledge. Well, gosh, I've thought a lot about knowledge and how to represent it computationally. You know, knowledge, I think, is something that I would say knowledge is a pretty human thing. That is, in our efforts in Wolfram language, for example, to capture computational knowledge, to capture things about the world, things about mathematics, whatever else, one feature of what we're capturing is it's not all the possible things that can happen. It's not all possible computations. It's things we happen to care about. Now, that might be knowledge about primes. It might be knowledge about movies, but it's things that it's not, we're not saying, we're not capturing in there what are all the configurations of atoms that exist in the world. We're saying there's a configuration of atoms and it corresponds to the Washington Monument or something. And that particular configuration of atoms we consider interesting. The one that is the configuration of atoms that's this lump of air that's somewhere around wherever, we don't consider that interesting. We identify as these symbolic lumps of knowledge, these things which we have considered as a result of our civilization to be important. And so I think knowledge is intimately tied to kind of what we have considered important in our civilization. It is not sort of the arbitrary, it is not something where the arbitrary computation is not really about knowledge. The arbitrary configuration of things in the universe isn't really about knowledge. Knowledge is a human-tied thing, I think. And so in that sense, we're capturing, you know, to get to knowledge, you have to get sort of all the way to humans, I think. And I think in a sense, what we're trying to do, as I've said a few times, is sort of we're trying to bridge this thing between what humans can understand, what computers can represent, and how the physical world works. And Jonathan looks like he has a comment to make.
Well, I was thinking one of us should probably talk about branchial black holes with respect to knowledge.
Sure, talk about branchial black holes.
Okay,
that's very different. That's a very different take on knowledge than what I've just been talking about. Go ahead.
Right, but it is at least a form of it that's consistent with our models. So I should say, and this is actually not unrelated to the sort of consciousness question that Stephen was talking about earlier, that each sort of level of graph that we consider sort of gives you a new intuition for what it means to be a conscious observer with respect to our models. So in the causal graph, a conscious observer is effectively one of these relativistic hypersurfaces. So in other words, you can think of you can define a conscious observer in the relativistic case as someone who sort of views a bunch of space-like separated events as being simultaneous, as Stephen kind of alluded to. In the case of a multi-way graph, Then you have this branch-like hypersurface. That's the notion. That's our notion of a conscious observer. So then you think of the observer as being like an entity that makes an equivalent, that views a bunch of distinct quantum states, a bunch of states in the branch-like hypersurface as being somehow equivalent. And then when they try and perform a measurement, that's kind of isolating one of those states. And similarly, in the rulal space, you think of an observer as being a hypersurface in the rulal space, and then so therefore they're some entity that somehow views a bunch of different rules as being computationally equivalent. So in each case, the observer is some time-ordered sequence of equivalence classes between different kinds of states. So the interesting thing is that gives us a way of representing what it means for a conscious observer to have memory or knowledge. So in the quantum mechanics case, the way that it can work is you say the generational multi-way states, which are these things we talked about earlier, which if you don't need to know sort of the details of how they're defined, but basically they're the things that get walled off when you perform a quantum measurement of the kind that Stephen was describing in the live stream yesterday and earlier today. So if you perform a quantum measurement, you basically freeze time around a state. That's a kind of generational multi-way state. And one of the rules of the multi-way evolution graph is you can kind of only make measurements of states of the kind that you've already seen on previous hypersurfaces, because the generational multi-way states get generated from a superposition of states that occurred on a previous hypersurface. So in other words,
Jonathan, this is the philosophy one. You can't assume people understand quantum superposition here.
Fine, okay.
But keep going. Well, I might try and decode this in a minute.
Yes, no, but please do. So one of the things that means is you can kind of, as you progress through time in the multi-way evolution graph, the kinds of experiments you can set up, the kinds of observations you can perform are informed by and get more sophisticated as a result of the outcomes of previous measurements and observations. So you can think of that as being a minimal model of the observer kind of learning what things are true and how to set up better experiments. The same thing occurs in rulal space. So in much the same way as you set up a multi-way black hole around the state when you perform a quantum measurement, when you kind of develop a theory, when you increase the sum total of your knowledge with respect to rulal space, you are effectively producing a rulal black hole. These correspond essentially to pockets of computation. The majority of rulal space is computationally irreducible, which means it takes, it's sort of causally connected, but it takes an irreducible amount of time to travel from one point in space to the other. But sometimes you can produce a region that's causally disconnected, and those are like the pockets of computational reducibility. And so you can think of sort of an ultimate abstraction of the process of doing scientific investigation is the construction of these rulal black holes wherever they're possible. Wherever there exist pockets of reducibility, you're trying to construct kind of black holes in rule space around those pockets.
Yeah, that's very interesting, a very different end of the story from what I was talking about. I mean, basically what you're saying, so another way to think about what you're talking about is you're asking for a very low level kind of machine code level version of what knowledge means in terms of, can you to what extent can you take the sort of microscopic degrees of freedom of the universe and kind of aggregate them into something which you can view, you can describe at a sort of higher level. And that's kind of what you're talking about as a kind of I suppose in some sense, it's to what extent, ultimately what we try to do with things like language is to turn all the complexities of the world into this simple symbolic representation of what's going on. That's a very human end. That's the very human end of making knowledge. A very machine code end of making knowledge is, let's take these little micro operations that were going on and let's find a way to aggregate together some number of those micro operations. And that's I think what you're talking about. And that's actually, I mean, it's pretty interesting to look at. That's more like kind of coarse graining in statistical mechanics, things like this. It's a different end of the story. It's the less human end, the more physics and computation end of the story. But that's quite interesting, and probably one should. There's a pretty big distance between those, but it's quite interesting to look at both of them. Let's see. What is randomness? Is it like the possibility to act against the laws of the universe? Okay, so we in this model of physics, there is no, quotes, true randomness. Everything is kind of determined. So I have a friend named Greg Chaitin, who was one of the originators of algorithmic information theory. And in algorithmic information theory, one's interested in saying, one's interested in sort of assessing how random something is by saying, how long is let's say you have a string of numbers. You can say that the string of numbers is truly algorithmically random if there is no program that will make that string of numbers that's much shorter than the string of numbers itself. Given the string of numbers, you can always have a program that is basically just contains the string of numbers and just says, here it is. That's what the program does. But that program will be the same length as the string of numbers. So a general question, it's sort of a general question of modeling and fitting and so on, is can you have a description of that string of numbers that's much shorter than the string of numbers itself? If you can have a description that's much shorter, then you say it's not random because I've got this short description. Okay, so in that sense, for example, the digits of pi, which as far as we can tell statistically, seem completely random. If we say, oh, they're the same number of ones and sevens in the digits of pi, yeah, they're the same number of ones and sevens. But at an algorithmic randomness level, the digits of pi aren't random because after all, they just come from that simple program which says you generate the digits of pi using this algorithm. So they're not algorithmically random, but they may be apparently random. Okay, so my friend Greg Chaitin has this number that he constructed long ago, probably in late 1960s, early 1970s. He calls capital omega. And capital omega is a truly non-computable number. It's not like pi, where you can just generate the digits by this sort of simple program. Omega is the halting probability of a universal Turing machine, and it is a number where no digit of that number can be computed by explicitly running a program. Every digit of that number is intrinsically has to come from outside of a sort of computational universe. So Greg's omega couldn't be made in our universe. We couldn't know that number in our universe. So a long-running question that Greg and I have debated is the universe like pi, where essentially there's just a rule and you generate the digits of pi, just like in the analogy of the universe, you just generate the behavior of the universe progressively from that small program, or is it like omega, where you really can't generate it, you just have to be given it, at least as far as the rules of something like a Turing machine are concerned. And so what one might say is the sort of true randomness, in some sense, true randomness is this algorithmic randomness, where there is no way to compress it. There is no way to give a program that's shorter than the thing itself that will generate it. Now, you can still have effective randomness. You can still have something where you can't go decrypt it in any computationally feasible way, but where nevertheless there is in principle some small program that produces it. So in this theory of physics, the universe is just not algorithmically random. The universe is algorithmically, comes from it's a simple rule, let's say simple initial condition, generates the whole universe. So there isn't algorithmic randomness in the universe in this model. And so it's, yeah, so I mean, that in that sense, there are no miracles. You can't act against the laws of the universe because, the universe is just determined by some rule, and there is no kind of outside the universe randomness that's associated with it. I mean, I'm always a big complainer of models that have lots of randomness, because randomness in a typical model is an admission that there's something you don't know about the system. Like let's say you say, well, we'll just add this random variable here. That really means there's something that's affecting your system from the outside and you can't describe it. If you could describe it, you wouldn't say it's a random variable. You would say, well, here's the mechanism by which it does what it does. Okay, from Craig, why do we experience time as linear in this model? Okay, that's interesting. So one feature of these models is I think they finally explain some mysteries about time. And time in these models is really the passage of time is the doing of irreducible computation. So in a sense, as time progresses, what's happening is the universe is computing the next step, the next step, the next step. And that is an irreducible computation. You can't really shortcut the computation. And so the reason there is a passage of time is because there is a succession of steps of the computation. And our psychological time is the sort of inexorable execution of those steps of computation. Now, what's interesting is that the arrow of cosmological time, defined by things like the expansion of the universe and the increase of entropy in the universe, the increase of randomness in the universe, that is aligned with our psychological time. We see the universe expanding, not contracting. We see things getting more random, higher entropy, not lower entropy. We don't. It doesn't suddenly happen that we are psychologically misaligned with the things that happen in the universe. Well, in this model, that's explained because basically we're all made of the same stuff. We're all made of this. We're all part of this inexorable computation that's happening, and this arrow of time is shared in this computation between what happens to us psychologically and what happens to the universe as at a cosmological level, and so on. Okay, there's a question about, Brian is asking, what does the model say about simulation? We tried to answer that yesterday, actually, as well. I mean, I think I'm going to get better and better at answering that question, because I think that question is going to come up over and over again. I think we had one version of that is this question of sort of, what does it mean to be in a simulation? Might mean, well, the universe is a computation that's running on somebody else's computer. We don't think that's the case. The universe this model is simply a description of what the universe does. Another thing that one might mean by one's in a simulation is somebody intentionally made the rules for the universe. I think that notion of sort of extending intentionality to these rules is really, really far off. But the real killer, as far as I'm concerned, is this rule-space relativity idea. That, in a sense, the creator of the universe, if there was a sort of the simulator of our universe, didn't really do anything, because all possible rules that they might have used are equivalent in being able to give our universe. And the fact that we perceive some particular set of rules is a consequence of the particular way that we describe the universe. That's very much us. That's the us that we are living within, so to speak, that is causing us to describe the universe this way. So the simulator, the game designer that designed the game for the universe, they don't deserve a big they don't deserve a big bonus or anything, because they didn't really, or a big paycheck. They didn't really do anything. They could have written down any rule, and that would be they could have that's sort of a rule for the universe. They didn't elaborately construct and weave sort of the reality that is our universe. They could have picked any rule, and it would have made our universe. And we as entities within that universe would perceive it, would be able to perceive it the way that we perceive the universe. Let's see. I'm not going to click this link here. So if that for the folks who are driving this live stream, if I should, give me the text of whatever that whatever that link is. From Siesta. Okay, if the universe is computable and we find a model for it, what are your thoughts on the ethical implications of running large-scale simulations that could one day potentially create life? Okay, that's an interesting, that has a bunch of questions within questions. So, I mean, I think, as I mentioned, sort of the definition of life is a difficult one, but I think one of the ways that we talk about ethical implications, we've got AI, and the question is, what are the ethics of AI? And at what point is it the case that, for example, AIs have rights, and we owe an ethical duty to AIs? We view in the current world our ethics, we think we have an ethical responsibility to other humans, maybe to some animals. Do we have an ethical responsibility to the planet? That's a weird and complicated question. Do we have an ethical responsibility to the internet? as an abstract thing, another complicated question. Do we have, when we create an AI, at what point will we say we have an ethical responsibility to that AI? And for example, if that AI is the disembodied thoughts of a person, then we might say immediately, you jump and say, of course, well, if that AI is, the disembodied thoughts of a person created by, I don't know, taking their brain and uploading the simulation of their brain to the AI, you might say, well, then sure we have some ethical responsibility to that. Do we still have the ethical responsibility if we can make a large number of copies of that simulation of the brain? That's clear. Do we have, what makes us have a sort of ethical responsibility to the AI? Does it have to be the case? If we can talk to the AI, is it, for example, there was a company that made one of these, actually they used the Wolfram Alpha API to provide knowledge for this thing. It was a desktop robot type thing that you could talk to, and it would remember certain things about you and so on, and it could answer questions about the world using Wolfram Alpha and things like this. And the question was, the company went out of business, and these were sort of cloud-based devices, and at some moment they started going offline, they started disappearing, along with their various memories and so on. And the question was, in some sense, what are the ethical responsibilities to those devices? Well, really, it has a chain of sort of ethical story, because those devices stored memories about humans, and one might have an ethical responsibility to those humans. And I'm really bad at doing real-time ethics here. I'm bad at doing probably philosophical ethics at the best of times, and probably I'm no good in real time. But I think the interesting question is, what will cause us to decide that AIs should have rights, when we should have an ethical responsibility to them? For example, another person I knew, a company that unfortunately hasn't made it, but it's kind of a cool idea, was going to start putting essentially bots on social media platforms and so on, and these bots would own themselves. So the bot would, like, for example, it would develop jokes based on AI, and it would start telling these jokes, and it would start having a channel, and it would start having it would tell these jokes. Maybe it would have a Patreon, channel. Maybe it would have a thing where it runs ads against its jokes or something, or it tries to give people kind of upbeat advice or whatever else, or make kind of comments on their feeds and so on. And so this bot could be a completely disembodied thing. It's just out there running on some cloud server somewhere, and it's just a thing out in the social media world. And the question is, at what point does this bot get to the point where it should be considered to have rights? And for example, is it objectionable for, I don't know, Facebook to say, you're a bot, we're shooting you, we're closing you down? Does there come a point when that becomes ethically questionable to do that? When this bot autonomously has generated within itself lots of knowledge about the world, it's become a very wise bot, and it knows a lot of things. It can have an interesting conversation with people. It can put up it can create, art in a wonderful way. At what point do we switch off? Do we think it's okay to do we always think it's okay to switch off the bot just because it's a bot? Or do we say, if it can, paint great paintings, then it's no longer okay to switch the bot off? So those are questions I don't think we have answers to. I think that one of the things, I kind of think that things like computational irreducibility and so on, in the future of kind of the way our world works and the way that we choose to run the world, things like computational irreducibility, which might seem like some kind of geeky sort of abstract thing, they will be incredibly central to the issues that we actually have on an everyday basis. I think that this question of what should the AI constitution be like? If we could determine how AIs should work, what should we tell them? We certainly we could use the Asimov laws of robotics, but they're way too simple and they won't capture things. I think in the end we're kind of enmeshed with Gödel's theorem and so on and computational irreducibility, saying there'll never be a small system of laws that will constrain the operation of the AIs to be just what we want and nothing but what we want. And I think it's rather similar to human laws, where we end up with these really complicated codes of what's considered legal and not, because it is inevitable in this world that it has computational irreducibility that we kind of have to have all of these elaborate patches. There's no universal, there's no one law that kind of governs them all and that allows us to say what we think is good and what we think isn't good and so on. So long answer to that kind of question. Okay, I'm gonna skip ahead a little bit here. Let's see. Okay, Kelly is asking if consciousness doesn't arise. If consciousness doesn't arise in itself, did it really model the universe well? You know, the problem is, point to a bag of bits and say this is consciousness. It's hard to do. In fact, I think it's impossible to do. I think that it isn't a, it's to kind of, you know, it's like the sequence of life, intelligence, consciousness. These are all complicated concepts defined, if anything, more historically than by virtue of this is an abstract thing. Now I have a test to determine whether it satisfies this. I think it's a very, you know, it really isn't something that we can, you know, to ask the question, does, you know, like, for example, you know, to go from the kind of very, very, very low level machine code representing the universe at scales of, you know, 10 to the minus 93 meters and so on, to go to the point where a frog jumps out is a very long way. And it's not, and computational irreducibility, there's a thick, I think, a thick wad of computational irreducibility between those things happening at 10 to the minus 93 meters and the things at the scale of a frog jumping out. And I think it's the same type of thing with what we perceive as being consciousness, which is a very human thing. If consciousness was something abstract where we could say, this bag of bits has consciousness, well then sure, we might easily be able to see that arise. But by the time we have to build whole humans, they're more complicated than frogs, and it's a long way to get to that. Now, having said that, I think computational irreducibility is sort of the thing you need to have something like consciousness is computational irreducibility, or more specifically, sort of computation that I have this idea of the principle of computational equivalence, which is a notion of equivalence between different kinds of computational systems. Once you've reached the level where you have this sort of equivalent computation in which there is computational irreducibility, then I think you have satisfied the core requirement for consciousness. Consciousness, as we describe it as humans, is something for which you need the whole elaborate human structure to build it up. But consciousness, the underlying mathematical requirement for consciousness, I think, is computational irreducibility, and that's extremely easy to achieve in one of these models. Here's a comment from Gaydon. Consciousness constitutes both subjectivity and objectivity, and thereby makes the latter accessible to the former. Oh boy. I mean, I think that is a kind of a view of consciousness in which there's kind of an inside looking out as opposed to just an outside looking in. And I think Jonathan mentioned in a rather mathematical way the kind of notions of consciousness that exist in our models in terms of this kind of way of describing the world in terms of observers who have certain kinds of access to certain kinds of knowledge about the world and synthesize certain kinds of knowledge about the world. So I think that's our best hope for being able to unravel that question of sort of subjectivity versus objectivity. It's kind of this notion that really does exist critically exists in these models, that the observer is embedded within the system, and you have to only be talking about things that an observer embedded within the system can deal with. You can't say, oh, we can look from the outside, the kind of you know, the kind of God's eye view of the universe, looking from the outside, so to speak, and being able to say that's objectively what happened. It's all subjective in the sense that it is from entities within the universe. Okay, it's a question, how do the rules of logic manifest in our computation? So, well, logic is a very specific kind of axiom system that is an idealization of human thinking. it's a very coarse idealization of human thinking. It's the one Aristotle kind of invented as a way to sort of characterize pieces of human argumentation. If A, then B means if not B, then not A, and things like that. Those are sort of the rules of logic, which are an attempt to capture kind of the some sort of essence of human argumentation. Those have been turned into more mathematical kinds of constructs through people like George Boole in the 1830s. The Boolean algebra is a sort of more mathematical version of that. Actually, so those systems are axiomatic systems. They can be thought of as things like, P or P is the same as P. If it's raining or it's raining, then that's true if and only if it's raining. So then you can ask questions about how do you get that kind of logic, that kind of axiom system that represents logic, how do you get that from, where does that come from? Well, I claim it's really a human construct, but you can ask, what is that axiom system? What's the simplest representation of that? If you look in the space of all possible axioms, what's the simplest version of that? Well, I actually found that in the year 2000. I found the simplest axiom system for logic. It's a really tiny thing. It's just got 6 little NAND operations and 3 variables in it. And that single statement, from that single statement, you can derive all of logic. So if we ask ourselves, where is that in the, is that something that can arise in, can we sort of have logic show up as an axiom system? The answer is yes, it's about the 50,000th axiom system, just enumerate possible axiom systems. How does it relate to these models of physics? Well, that's kind of interesting. I think that these models of physics, like that axiom system, really have kind of a family resemblance in the sense that they too are sort of rules that define what happens. Logic involves these axioms that say that kind of give you constraints on what on what you can make as a logical deduction and so on. So I think it's sort of the concept that there is a precise version of things that operates according to rules, that's very much burnt into this kind of model. The particular rules of logic, I think, are kind of arbitrary and are very much a human construct. We should wrap up soon, but I'll try and take a few more of these. Let's see. Okay, so Connor is asking, once we have an answer to what the fundamental rule for our universe is there any is there any hope of understanding why it's that rule? Now, I mentioned this a few times here. I mean, that was the thing that I really wanted for a long time. And what I've realized just in the last month or so, as we've developed this idea of rule-space relativity, ruleal relativity, is this point that actually it isn't that it's why this rule and not another. It's really any rule, that they're really all these rules are operating, and you can pick any one as your description of the universe. But what you're doing is you're picking a rule that works given the description language that you have for the universe, given our particular kind of sensory data, sort of the physics we built up and so on. And so really then what you're asking is, why is this particular rule the one that sort of dovetails with our particular human way of thinking about things? And so, I've spent a lot of my life as a designer of computational languages, and I've been interested in this question of computational language is all about bridging between what humans choose to think about and what computers can do, and figuring out what are the primitives. Computers can do all kinds of things. They can generate all kinds of possible rules, all kinds of possible behavior. Which ones of those do we care about? Of all these possible computational operations, which one should we define words in our language to talk about? Which ones are we going to actually, as humans, want to do things with? That's what computational language design at an essential level is all about. And that's the so really what's going on here is we've got this 3-way description. We've got the rule that we're using to describe the universe. We've got what the universe is at. We've got sort of the computations and the way that we think about computation, and we've got sort of human thinking. And this is really a question of when we look at why this rule and not another, we're really asking, why is this rule the correct? Why did our human thinking work in this way so that we ended up attributing this rule to be the thing that is our description for the universe? So it's in a sense, it's putting the spotlight back on us and saying, okay, why did you pick that particular? Why did human civilization evolve in that particular way? Why did biological evolution choose to make our brains evolve in just such a way? So a comment from Juan here: if the hypergraph is enumerable, is the axiom of choice really a concern? Well, no, as Jonathan described there. Anna here. Okay, can randomness be a derivative of error or noise in the system? Can the universe generate mistakes? Well, the answer is no. What we're saying is there is a definite rule, and that is the story of the universe. The universe is just running this rule. The operation, what the universe does is what this rule says should happen. Now, we could say, well, our description is a bit incomplete. There can be this randomness on the side. There can be this miracle that happens. There can be this noise that's operating on the system. That's something where we say our description of the universe isn't complete. There's something we have to add to it that we will call noise, or we will call a random perturbation. We're saying, no, you don't need to do that. You don't need to say there's something beyond the description that we give. Now, if you say, well, let's only look at a part of the universe, even with the description that we have, then sure, you would be saying the other parts of the universe might be operating on the part that we see by applying noise to that part of the universe. But no, in the way that we're talking about, this is really supposed to be kind of the whole enchilada. This is kind of this is the full thing where we're saying it's this rule run in this way, and it just makes the whole universe, and there's no extra little wiggle room around the sides. Okay, we should wrap this up here. I just want to say that, well, I thank you for all these interesting questions. Oh, okay, I'm just going to take this one because it's fun. From Juan here. Computation, as we think about it, requires energy consumption. If the universe is constantly computing to hold space together, would it be consuming lots of it? Okay, that's an interesting one. So first of all, computation does not intrinsically require energy. It was a thought, actually, von Neumann was responsible for this kind of mistake in the end, that said that when you do ordinary logic, you say there's an AND operation and it has two inputs, P and Q, for example, but there's only one output. And so that is a sort of entropy reducing thing. So you can think of it that it's an irreversible step to go from those two inputs to one output. Turns out you don't need that kind of irreversibility to do meaningful computation. But so you don't need to spend energy to do computation. In our computers, as we have them right now, we do spend energy. Now, there may in fact be something, and actually I bet Jonathan could jump in on this, there may actually be something when we think about quantum computation that we have to spend energy in quantum. In fact, yes, this is something we have actually established here, that in quantum computation, to maintain sort of coherence, you have to expend energy. We haven't really explored that as much as we could, but that's kind of a story of making quantum computers that in order to prevent degrees of freedom kind of sort of decohering your quantum system, you actually have to spend energy to make that happen. So that does mean that there's an expenditure of energy in maintaining a quantum computer, so to speak. But in a traditional classical sort of computer, you don't officially need to expend energy in it. Now, so this question of is the universe, if the universe is constantly computing to hold space together, doesn't that mean it's using energy? That's kind of a very beautiful thing because we're saying that energy actually is the density of these causal edges. It is the computation. So in some sense, we can attribute, and actually this is something we should look at more, we should attribute, energy is a representation of the doing of computation. So in a sense, the density of energy is also the density of computational work. And actually, that's quite interesting, and I haven't really thought about that. But so that's saying that it's not the expenditure of energy. That's not that the energy is dissipated. It's that the very density of energy is the density of computational work that's going on. And that's an interesting thing. And that's a good segue to tomorrow's live stream, which will be about computer science and theory of computation and the way that relates to what we're talking about. And we might try to talk about, we may end up with our first guest tomorrow, talking a bit about how some of the ideas from distributed computing might be sort of ported to thinking about physics. Let's see, what else am I supposed to mention here? Okay, so tomorrow, 3 p.m., we're talking about computer science. That'll be a technical discussion. And then on Friday, oh, wow, that's fun. I am scheduled to do a fundamental theory for kids briefing. So I've been doing, in the past weeks, while we've all been pandemicked, so to speak, I've been doing some science Q&As for kids, and sometimes having to give a hint. Last week, for example, when people are asking questions, when it's, gosh, I think I know the answer to that, but it relies on this new fundamental theory of physics. So I was kind of having to say that a few times. And now we get to, because we've described this theory a bit more, we get to, and the theory is out and about. It might be easier to answer some science questions, but I'm going to do a kind of a rundown on what we think we know now about fundamental physics, based on this theory for kids. And that's, for me, it's a lot of fun, because it's really a fascinating exercise in being able to say, what really am I talking about? Can I really turn this into something where we don't have to talk about space-like hypersurfaces to get the point across? So anyway, that'll be Friday at 3:30 Eastern Time. All right, well, thanks very much for lots of terrific questions, and look forward to hearing from you all another live stream. So thanks a lot, and see you later.